The next thing we're going to look at here are differentials. And the overall basic idea here is that differentials considers dx and dy to be tiny variables of their own. Okay, little variables called differentials. Okay, so the definition for this is that if we are given the function y equals f of x, then we can define the differential. So the differential dy is defined by the following. Dy equals f prime of x times dx. Okay. So actually here in this definition, we have one differential dy being defined in terms of another differential dx right here. They are linked to one another. So another differential. And so you'll notice if we're considering like dx and dy, these differentials are like tiny little variables. This little tiny variable dy depends on what is going on with dx and also what's going on with the derivative f prime of x. So dy is very much like a dependent variable here. So dependent variable because it depends on the values of other things. Depends on what dx is, and it also depends on the value of x because the derivative evaluated at that point of x is part of our differential formula there. Okay, now where have we seen these before? You might know. Dy and dx come up real often in one of our favorite notations, you know. It's the Leibniz notation, dy dx, which means the same exact thing as the derivative f prime of x. So we've seen lots of differentials already without even really realizing it anytime we use this Leibniz notation. Okay, so Leibniz notation is a ratio of differentials. Surprise. So you knew what differentials were all along. Okay. Now let's look at a little example here. We're going to consider the function y equals x cubed minus 3 cube root of x. Lots of threes going on there. Let's start with our rewriting of this as we typically would. So that is x cubed minus 3x to the 1/3 power. Okay, we are going to find the differential dy. And really all we need to do for that is to find the derivative. Dy dx equals f prime of x, which we can just power rule on that. That would be 3x squared minus, well, 1/3 times 3, that would be 1 x to the negative 2/3 power. And then to get differential dy solved for by itself, just multiply on both sides by that little dx differential. And you'd come up with dy equals 3x squared minus x to the negative 2/3 times dx. And that's how we would define that differential dy. That's all there is. But now in the next part, we can actually evaluate that differential. So we're going to evaluate the differential when x equals 1 and dx equals 0.05. Okay, so dy equals, I'm just going to rewrite our little equation that we found there, 3x squared minus x to the negative 2/3 times dx. And we have been given values for x and dx. So plug those on in. 3 times 1 squared minus 1 to the negative 2/3 times our dx there, which is 0.05. Okay, and so we get 3 minus 1 here, because 1 to any power is still just 1, times 0.05. And so that would just be twice 0.05, which would be 0.10, 0.10 for the value of dy. Okay, so that is finding the value of that differential. Now, geometrically, let's look at what's going on with differentials in general and why it's in this particular section, 3.9. So dy and dx, geometrically, these refer to tiny changes along a linearization. So along the linearization of f of x. Okay, so let's make a little sketch here of a function and its linearization. Let's make a nice generic function here. Call that f of x. And let's pick a particular point to look at. We'll call that x. And then we'll draw in the linearization, aka tangent line for that function at that point. Would look like this. Okay, so there's our L of x. And so if we make little changes along that linearization, let's say we've moved from the point where we set the linearization up a little bit to the right here. Let's just make a small change in that direction. And that little change over that way would be called dx. Okay. And that little change in x causes movement along the linearization. Okay, if x moves that far, your point on the linearization would be up here. And so that in turn has caused a little change in the y direction. And that is our differential dy. Okay. And so that's why this all ties together so much, why the tangent line and the linearization all relate to the derivative, and dy dx is notation for the derivative, all of this. It's because that slope really ties everything together. The slope of the tangent line, aka the linearization of our function, would be just change in y over the change in x, rise over run, okay? And that is what we end up calling the derivative. So that just brings everything back together there.